Hi, this is Sir Aris. Let us talk about Chapter 3, Second Order Linear Equations. We'll be covering sections 3.1, Homogeneous Equations with constant coefficients, and 3.2, Solutions of Linear Homogeneous Equations and the Wronskian. Generally, a second order differential equation can be written by this form where f is a function of t, y, dy by dt. Typically, t is our independent variable. This equation is linear if the function f is of this form, that is, if f is linear in y and dy by dt, and g, p, and q here are functions of the independent variable t, but they do not depend on y. We can generally write a linear second order ordinary differential equation as y double prime plus uh, pty prime plus qty equals gt. Here the prime denotes the differentiation with respect to t. Alternatively, we can multiply both sides by pt and then combine the constants. So you have pty double prime, qty prime plus rty equals gt. Here we will restrict to intervals in which p, q, and g are continuous functions. Um, an initial value problem consists of the a differential equation such as 3.1, or this general expression, 3.3 here, or 3.4, and a pair of initial conditions y at initial time t sub 0 equals y sub 0, and the derivative y prime at t sub 0 equals y prime at y sub 0 prime. We get two, we need two initial conditions because for a second order differential equation there would be also two integrations involved. Um, a second order linear equation is said to be homogeneous if our expressions here 3.3 and 3.4 have g, small letter g and capital letter G equal to 0. So we have here, for example, using 3.4, that um, the this expression can be written like this. So we remove the g here, we set it to 0, and we focus on when p, q, and r are constants, or we write it like this. So a, b, and c are given constants. Now let's try to solve a simple equation, this one. So here we can easily write y double prime equals y, and think of an expression or a function wherein if you take the derivative, here in this case the second derivative, it gives you back the original function. The main candidate would be exponential functions, or exponential. Y equals, say, um, some constant, let's say c1, e to the power of t. So if you take the derivative, it is just y. Take the second derivative, it's still equal to y. Also, we can have, let's call this y1. Another option, y2, is still an exponential function, c2 e to the minus t. So generally, we have a solution y equals c1 e t plus c2 e to the minus t. If you want to verify that this is indeed a solution, we can take the first derivative, that would be c1 et plus c2 minus 1 e to the minus t. And then the second derivative, c1 et plus c2 minus 1 times minus 1, that's 1 e to the power of minus t, which is just equal to y. Now, if you use our boundary or initial conditions, so you have y 0 equals 2. So in that case, this y sub 0 here, or y, would be equal to c1 e to the power of 0 plus c2 e to the power of 0. So that would be, this is equal to 2. So that's c1 plus c2 equals 2. The second bound, initial value would be, or initial condition is y prime 0 equals minus 1. So we have y prime equals c1 here, e to the power of 0 plus c2 minus 1 e to the power of 0. This is equal to minus 1. So you have c1 minus c2 equals minus 1. And we have these two expressions that would give us c1 plus, or c1 plus c2. Let me write it here. So c1, this is equation, let's call this equation 1 and equation 2. So adding the two, we have c1 plus c1 equals 1. So if you add 1 plus 2, so this gives us c1 equals 1 half. Okay, and then knowing that, say using 1, c2 equals 2 minus c1. So that would be c2 equals 2 minus 1 half, or 3 halves, which then finally gives us y equals c1 et, so that's 1 half et plus 3 halves e minus t. Okay, so generally, let us consider the more general equation a y double prime plus b y prime plus cy equals 0, whose coefficients a, b, and c are arbitrary real constants. We start by seeking exponential solutions of the form y equals ERT, where r is a parameter to be determined. So for given this y, we can use y prime equals r ERT and y double prime as r squared ERT. And then substitute this to this expression. You have a r squared ERT plus b r ERT plus c ERT equals 0. Factoring out ERT, you have AR squared plus BR plus C times ERT equals 0. This here is our characteristic equation of this differential equation. And since this part is not equal to 0, then this characteristic equation should be equal to 0, or that AR squared plus BR plus C equals 0. The solutions are, possible solutions are of three types. One is that they are real and different. The other one is that they are real and the same. Third one, um, complex numbers. Okay, but we focus only on, so we focus uh, on one for this section. So there, the solutions could be, so the solutions are, so if you only focus on one, the solutions are R1 and R2, where R1 is not equal to R2. Okay, so Y is simply, there's one solution, let's call it Y1 equals C1 e to the power of R1t, and another solution Y2 equals constant C2 e R2t. So the general expression is Y equals C1e R1t plus C2e R2t. If you want to verify, let's take the first derivative. That's C1 R1 e R1t C2 um, R2 e R2t, and the second derivative C1 R1 squared e R1t plus C2 R2 squared e R2t. Okay, now if we plug that these values to our original expression ay double prime plus by prime plus cy, that would give us, let's say we want ay prime plus by prime plus cy equals 0. Let's say we'll try to plug in this term, this term, and this term to this expression. We will see um, a or c1, okay, a r1 squared plus br1 br1 plus c, okay, plus c2 a r2 squared plus br2 plus c. Okay, so here we have this ar1 comes from here and here. br1 would be b and this, and c would be this. Okay, and then a r2, this one, b r2 is this, and c here. This one is e to the power of r1t. Here it's e to the power of r2t. Now since this is 0 as well as this, then this is equal to 0, which verifies this this solution. Okay. If we can also include initial value, initial conditions, but we can, the values of C1 and C2 will then just follow. So let's try to find the solution of this initial value problem. Y double prime plus 5y plus 6y equals 0. The characteristic equation is given by 1 plus 5, so that's 1a, no, that's 1 plus 5 This one is r squared plus 5r plus 6 equals 0, which is simply r plus 2 times r plus 3. And then the solutions are r equals minus 2 and r equals minus 3. Let's call this r1. This one is r2. Okay, so the solution would be y equals c1 e to the power of minus 2t plus c2 e to the power of minus 3t. Using our initial conditions, let's say, or taking the derivative, maybe let's use this initial condition first. So y at 0 equals c1. This becomes this 0, so that's e to the power of 0 plus c2 e to the power of 0 equals 2. So we get this expression. Let's call this equation 1. Now let's take the derivative of this. So we have y prime equals negative c1 to e to the minus 2t minus c2. This is 3 e to the minus 3t. And then the initial value y prime 0 equals 3. So y prime 0 equals minus c1 times 2 minus c2 times 3 equals 3. Okay, so that's minus 2c1 minus 3c2 equals 3. That's equation number 2. So to solve for c1 and c2, we can multiply c1, or equation 1, say multiply 1 by 2. So that gives you 2c1 plus 2c2 equals 4, and then add 2, 2. Okay, so if you add them, these two cancels, so we get minus c2 equals, here this would be 3 plus 4, that's 7. c2 equals minus 7. In a similar way, or if we use using 1, we have c1 equals 2, um, 2 minus c2. Okay, and you have 2 minus negative 7, that would be 9. c1 equals 9. So finally, we can write y equals 9 e to the power of minus 2t minus 7 e to the power of minus 3t. Okay. Um, Let me check. Okay. So now let's proceed to solutions of linear homogeneous equations. We have this again, an existence and uniqueness theorem. If we have this initial value problem, we as long as p, q, and g are continuous on an open interval that contains t naught, then there's exactly one solution of this problem throughout. It exists throughout the interval I. Now we often write a differential equation in terms of an operator L. For second order differential equation, we can write LD squared plus PD plus Q, where D is the derivative operator. For example, let's say L applied to Y. So Y double derivative plus PTY P here, and then the derivative D plus QTY. There's a principle of superposition, wherein if y1 and y2 are solutions of the differential equation, then the linear combination is also a solution. That is very easy to prove. We can write it simply as, say, if you apply L to C1y1 plus C2y2, that's simply C1y1 double prime plus PT C1y1 prime plus QT C1 Y1 plus C2 Y2 double prime plus PT C2 Y2 prime plus QT C2 Y2. So if this can be written as C1 um, Y1 double prime plus PT Y1 prime plus QT Y1, okay, plus C2 Y2 double prime plus PT Y2 prime plus QT Y, okay. So here this is supposed to be square brackets, or we have C1 L applied to Y1 plus C2 L applied to Y2. Now this 2 are 0, hence we have shown that this L applied to this superposition is 0, and the superposition is a solution. For the initial value problem, it follows that from the principle of superposition, the solution gives us this two, two equations comprising a system of equations. So our goal is to find C1 and C2. This is two-dimensional, or two equations with two unknowns. The values of C1 and C2 can be written generally in an equation, um, here written in determinants. So basically, we're using the coefficients of um, the, the terms in our equations. In the denominator, that's the coefficients, let's call it the coefficients of uh, the system, y1, y1 prime, y2, y2 prime, okay. Uh, Here, the numerator, we replace the first column corresponding to values of uh, showing that we are looking for C1. And here, since we're looking for C2, we change the second column with y sub 0 and y sub 0 prime. Let's call the coefficient W, or the determinant of the coefficients of the system, as W. The determinant is given by this expression. If this is not 0, so here the denominator, if they are not 0, then the solution exists. And we have a unique solution for C1 and C2, regardless of the values of y0 and y0 prime. And this determinant W, we call it the Wronskian determinant, or simply the Wronskian of the solutions y1 and y2. Suppose in this theorem, y1 and y2 are solutions, and there are initial conditions, then it is always possible to choose the constant C1 and C2, so that this satisfies the differential equation in the initial condition if and only if the run scan is not 0 at t sub 0.